Okay, let us start the session. So, very good afternoon, everyone. Just 1 second, let me check everything is fine. Yes. So, very good afternoon, everyone. My name is Ambuj. I am a research scholar at Agriculture and Food Engineering Department from IIT Kharagpur, and I will be taking your live interactive session for the course Computer Vision. This course is taught by Professor Jayant Mukhopadhyay from IIT Kharagpur. And what we'll be doing in this particular session, I'll be solving some of the numerical objective type of questions as well as some descriptive objective questions based on the previous week's content in front of you all. And what you have to do, you just have to take a pen and notebook, try to jot down all the necessary points, okay, which are there, and then at the end we will discuss what is the correct solution for the problem, okay. And in the later part of the session, in the next half of the session, I have prepared some Google Colab notebook, okay. In that there are some codes written, and I will be explaining you the correct procedure which you can follow for getting hands-on practice on these particular concepts, okay. So let us begin. The very first question for the present session is: consider three 2D data points x1, x2, x3. x1 is 2 comma 3, x2 is 4 comma 7, x3 is 6 comma 5. Then you have to calculate the population covariance matrix, and the formula has been given to you, which is 1/3 summation I equal to 1 to 3 xi minus x bar transpose. Okay, multiplication of both these factors. Okay. So do try to solve, at least try to jot down what is the question, okay, and which approach you would like to imbibe into it, okay, that you try to jot it down. Yes, now you try to see this, that the correct option would be A, 2.67, 1.33, 1.33, 2.67, okay. Now you try to see x vector, the x bar, okay, or the mean vector would be nothing but, since three data points are given, you just have to compute the average. You can compute it element wise also, okay. You can segregate it into xi's and yi's, okay. Xi's and yi's you can segregate also separately. Otherwise, you can compute it using the method in which I have done, okay. So x bar is nothing but 1/3 of all the values sum and then divide by the number of values. Average will be coming 4 comma 5. Now you try to calculate what is the deviation vectors. Deviation vector d1 would be x1 minus x bar, x2 minus x bar is the second deviation vector. Third deviation vector is x3 minus x bar. Okay. So accordingly, when you try to compute 2 minus 4, 4 minus 4, 6 minus 4, okay. And then you try to compute 3 minus 5, 7 minus 5, and 5 minus 5. Okay. So accordingly, the vectors would be coming minus 2 comma 2, 0 comma 2, 2 comma 0. Then you try to see here what is the uh, each entry of the covariance matrix, which is 1/3 of all di square sum. Okay. What is the deviation we have calculated in x direction? It is minus 2, 0, and 2. Similarly, in y direction or in another direction, it is minus 2, 2, and 0. So summation of all the deviations that you will try to compute. Okay. squares of deviations of all the values. So minus 2 whole square, 0 whole square, 2 whole square, sum divided by 3. Then minus 2 whole square, 2 whole square, then 0 whole square divided by 3. Okay. These would be your corresponding elements 1 1 and 2 2 of the matrix. Means the diagonal elements would be 2.67, 2.67. Now you try to compute what would be the first element, that is element number first row second column. Okay, that element as well as second row first column. Okay, these two elements would be nothing but the summation of all di's. Okay, while computing the product. Okay, so that would be nothing but di 1 upon 3 summation I equal to 1 to 3 di1 di2. Okay, so minus 2 multiplied by minus 2, 0 multiplied by 2 and 2 multiplied by 0, that you try to sum and then do one third of it. Okay, multiply 1 by 3 or divide the whole of the thing by 3. Okay, so it would be 4 plus 0 divided by 3. 4 by 3 is 1.33. Okay, so now your other elements, uh, element second row first column and first row second column, both would be equal to 1.33. So the correct option would be nothing but option number A. Okay. When you are having a set of multi-dimensional data points, your covariance matrix is the fundamental object, which is the fundamental matrix which tells you how each coordinate varies both by itself and with every other. Okay. So in context of your PCA principal component analysis, its starting point for finding the directions or the principal components that capture the most variance in your data. Okay, reducing the number of principal components so that the computation becomes easier. Okay, as well as we want to capture the most of the variance of our data set. Okay. What is your covariance? Covariance is variance of a single feature x. Variance of a single feature x measures how spread out its values are around the mean. Okay. So variance of x is nothing but 1 upon n summation xi minus x bar whole square of that, that is variance of x. And covariance is between two features x and y, measures how x and y measures whether or how strongly they vary together. So covariance xy is nothing but 1 upon n summation I equal to 1 to n xi minus x bar yi minus y bar. Okay. Covariance xy is greater than 0, then x is above its mean, y tends to be above its mean. Okay. If covariance x comma y is less than 0, they tend to move in opposite direction. And if covariance x comma y is approximately equal to 0, then they are roughly uncorrelated. Okay. This is your covariance. Now you try to build a covariance matrix. For an m-dimensional data set with n number of points, where xi belongs to relation m, okay, and I is from 1 to n, the x bar is nothing but the mean, which is nothing but 1 upon n summation I equal to 1 to n xi. Okay. Then center the data. This is the form of the deviation vectors, which is nothing but di equal to xi minus x bar. Okay. Then you try to form the m cross m matrix, which is 1 upon n summation I equal to 1 to n di into di transpose. Okay. D is m by n matrix. Columns are di. Okay. And diagonal entries are variance of x, and off diagonal elements are covariance of xi and xk. Population formula divides whole the value by n, and sample covariance, uh, when you view your data as a sample from some larger population, typically divides by n minus 1 to give the unbiased estimate 1 upon n minus 1 d transpose. Okay. So why is the covariance matrix so central in PCA? Because of eigen decomposition. Okay. Eigen decomposition, after eigen decomposition, you will get, see here, q into Q transpose. Q has orthogonal columns which are eigenvectors, and caret is diagonal with eigenvalues lambda 1 greater than equal to lambda 2 greater than equal to plus and so on. So interpretation, if you want to see each eigenvector Qj is a direction in feature space, its eigenvalue, which is lambda j, is exactly the variance of the data when projected onto Qj. Okay. And in case of your dimensionality reduction, keep the top k eigenvectors to capture most of the variance in just k dimensions. Okay. So first of all, if I try to say what is the recap of the computational steps, collect your data points into vectors xi and compute x bar, then compute the deviations di's xi minus x bar, then form summation 1 upon n di into di transpose, then diagonalize summation to find principal components. Okay. Coming to the second question, suppose you have centered data in 2D whose variance covariance matrix is this one, 3 2 2 3. Which of the following is the first principal component, that is the unit length direction along which the variance is maximized? Okay, you have to compute the first principal component. Okay, try to compute. Options have been already mentioned here. Okay, try to compute. Yes, now you try to see here. Okay, the correct option would be A. Okay, you have to find the first principal component, that is the unit length direction along which the variance is maximized. Okay, step by step formulation is there. First of all, you have to compute the eigenvectors of the matrix summation. Okay, it is denoted by the symbol sigma. Symbol can be anything, A, B, C, or any other value. Okay, you can denote the matrix with the help of any letter, Greek or even English alphabet. Okay, so that is why here I have written determinant of summation A minus lambda A equal to 0. This is the characteristic equation. Now you try to see what is the determinant of this entire matrix minus lambda I. So only diagonal elements will be subtracted by the value lambda. Okay, so it would be determinant of 3 minus lambda 2 2 then 3 minus lambda. So if you try to compute the determinant, it would be 3 minus lambda whole square minus 2 square. That would be equal to lambda square minus 6 lambda plus 9 minus 4. That would be equal to lambda square minus 6 lambda plus 5. Okay, so lambda will be equal to lambda would be equal to using the quadratic formula you can compute. Okay, 6 plus minus under root whole square 6 square minus 4 into 1 into 5. Okay, that would be 6 plus minus 4 divided by 2. Lambda 1 would be 5, lambda 2 would be 1. Okay, so first principal component corresponding to the larger eigenvalue is lambda 1 equal to 5. Solving for the eigenvector at lambda 1 equal to 5, you try to solve summation minus 5 lambda into v equal to 0. Okay, so 3 minus 5, 3 minus 5, 2 and 2, and then v1, v2. Okay, that is minus 2, 2, 2, then v1, v2 equal to 0. So v1 we will get as v1 equal to v2. Now you try to compute the norm. Okay, the convenient choice is making it 1 comma 1. Okay, it's now your choice. So at 1 comma 1 it is would be nothing but under root 1 square plus 1 square equal to under root 2, and v cap will be equal to nothing but 1 upon under root 2. Okay, then 1 comma 1, which is your exact option, option number A. Okay, next you try to see the next question. Suppose after centering a 2D data set, you compute its covariance matrix and find the matrix sigma equal to 3, 3, 3 to 2, 3. You further determine its eigenvalues to be lambda 1 equal to 5 and lambda 2 equal to 1. Okay. What percentage of total variance is captured by the first principal component? Okay. This is the question. Now you try to see here the correct option would be 83.3%, 5 by 6 into 100. Total variance is lambda 1 plus lambda 2, that is 5 plus 1 equal to 6. Variance captured by first principal component is 5 by 6 multiplied by 100, that is 83.3%. Very simple. Okay. Then you try to see the question number 4. LDA is a parametric method. If whether it is true or whether it is false. This is the question. Okay. So correct option is A. It is true. Okay. LDA makes explicit distributional assumptions or Gaussian class conditional densities with a shared covariance. It learns and fixed set of parameters, mean, shared covariance, and prior. So it is indeed a parametric method. So LDA is linear discriminant analysis. Earns its label as a parametric method because it begins by assuming a specific finite parameter model for how the data are generated, and then it learns those particular parameters directly from your data training set. So assumptions are LDA will assume that for each class K, the feature vector X belonging to the relationship R, okay, is drawn from a multivariate normal Gaussian distribution. Okay, it follows a Gaussian distribution given by this particular expression. And two key assumptions are Gaussianity and shared covariance. Okay, because we have committed to data come from Gaussians with these parameters, we call LDA as a parametric method. Okay. So parameters to estimate would be class mean, then shared covariance, then class priors. Okay. Although altogether it would be finite number of parameters mu1 to mu k, then summation sigma as well as pi 1, pi 2 and pi k. No matter how many data points you collect, you are still estimating exactly this same set of parameters. So parameter estimation using class priors is pi k, okay, using this particular expression, as well as the class means mu k, nothing but 1 upon nk summation xi. Okay, and shared covariance is 1 upon n double summation xi minus mu k, xi minus mu k transpose, product of these. Then discriminant function and decision rule, one of the Gaussian parameters are in hand. Once the Gaussian parameters are in hand, classification proceeds by Bayes rule. Okay, you compute the discriminant score for each class. Okay, delta x, which is log pi k minus 1 upon 2 mu k, then summation inverse mu k, then xt summation inverse mu k, because sigma is shared here and delta k x are linear in x, so you assign x to the class with the highest delta k. Okay, this is the thing here. Then parametric versus non-parametric. In parametric models like LDA, you commit up front to a distributional form which is Gaussian to and estimate a small fixed set of parameters. Pros is very data efficient, closed form class solutions, interpretable. Cons is if the true distribution deviates from strongly from Gaussian, performance may suffer. Okay. In your non-parametric models, you make few or no distributional assumptions and complexity grows within. Process it is flexible, can approximate arbitrary decision boundaries, and cons is it can require much more data. Risk of overfitting is there, as well as no closed forms might be obtained. Bottom line is because LDA starts by assuming data are Gaussian with unknown means and common variance. Okay, then estimate exactly those Gaussian parameters. The classification follows by closed form function of those parameters. Next is what is a common application of PCA in data processing, pre-processing? Is it classification, segmentation, dimensionality reduction, or feature selection based on class levels? Okay. Correct solution would be nothing but your option number C. Okay, dimensionality reduction. Dimensionality reduction PCA is most commonly used to reduce the number of features by projecting the data onto the top of the principal components. Okay, it will lower your computational cost, it will mitigate overfitting, it can help visualize high dimensional data in 2D or 3D. Okay, classification, no, PCA itself does not classify, it's unsupervised. Okay, you can feed PCA reduced features into a classifier, that is another case. For segmentation, no, this term is usually inferred in an image. Hot signal segmentation directly PCA is not applied here, and feature selection based on class labels, it is done in unsupervised learning. And ignoring class labels, it selects components that capture variance, not necessarily those most discriminative of classes. So this dimensionality reduction is hallmark application of PCA. Okay. Then you try to solve. Consider the given samples of two class problem. X1 is this particular one 4 comma 2, 2 comma 4, 2 comma 3, 4, 3 comma 6 and 4 comma 4, and x2 is similar way, it is given 9 comma 10, 6 comma 8 and 9 comma 5, 8 comma 7, 10 comma 8. Compute both the within class SW and between the class scatter matrices. Okay, try to compute. correct solution would be A. Okay. Correct solution would be A. Consider the given samples for two class problem. X1 is given, X2 is given. You have to compute SW and SB. Okay. So within the class, scatter is SW equal to S1 plus S2. Okay. That you try to see here. X1 has been given here as a matrix. X2 has been given. Okay. Then class means if you will try to calculate, mu1 is 1 upon 5, the summation of all the xi's. Okay. Which is, yes, which is 4 plus 2 plus 2 plus 3 plus 4. 15 by 5, that is 3. Okay. And similarly, 2 plus 4 plus 3 plus 6 plus 4 by 3 by 5. Okay. 19 by 5. 19 by 5 is, I think, 3.8. Okay. So mu1 for the first class we have computed, mu2 for the second class we have computed. Then within the class scatter SW will try to compute. Okay, scatter matrix is nothing but 1 upon it is nothing but summation x minus mu1 into x minus mu1 transpose. Okay, that you try to compute scatter matrix. Okay, and the simple covariance is s1 upon divided by n minus 1. Okay. So similarly, you try to calculate the covariance. Then class 2 scatter matrix H2 is summation x belongs to x2 x minus class 2 scatter matrix is S2 x minus mu2 multiplied by x minus mu2 transpose. Okay. So similar to that, you try to compute and then you have to divide it by in the same fashion S2 divided by n minus 1. Okay. N is 5 here, 5 minus 1 is 4. Okay, so similarly you try to compute. Then within class scatter, if you will try to compute, it would be nothing but S1 divided by 4 plus S2 divided by 4. Okay, so S1 plus S2, S1 and S2 you already have computed. Divide each of the element by 4 and then try to sum element wise. So you will get the uh, within class, total within class scatter SW. Okay. Then between class scatter is SB, okay, which is nothing but mu1 minus mu2 multiplied by mu1 minus mu2 transpose. Okay. So mu1 minus mu2, you try to compute, direct computation is possible. Okay. Then SB will be nothing but uh, in the similar fashion you will try to compute. Okay. Mu1 minus mu2 multiplied by mu1 minus mu2 transpose. Okay. So that you try to compute the exact option you would be getting as option number A. Okay. Moving forward, the seventh question for the present session. Which of the following statements is true about the relationship between PCA and LDA? Okay. You try to just take a note of it. Okay. And then we will proceed. Then we will see which is the correct option. Okay. The correct option would be D. Okay. PCA maximizes variance while LDA maximizes class separability. Okay. Why so? Because PCA, as I already have told you, it's an unsupervised technique that seeks directions or the principal components, capturing the greatest overall variance in the data without using any class labels, and LDA is linear discriminant analysis. It's a supervised technique that first finds the projections, maximizing the separation between known classes while simultaneously minimizing the scatter within the each class. Okay. So PCA's objective is to have a variance maximization while LDA's objective is to maximize the class separability. Okay. So PCA and LDA are both your linear projection techniques. They have fundamentally different goals. They use different information in the data. Okay. PCA is unsupervised. Yes, it is unsupervised. It treats every data point equally, ignoring any class labels or groupings. Its only concern is finding directions in the feature space along which the data exhibit the greatest overall spread or the variance. And LDA is supervised. It explicitly uses the class labels of each sample to find those directions in feature space that discriminate the known classes. Okay. And optimization objective is to maximize the variance. In case of your PCA, only objective is to maximize the variance that has been written here. PCA finds the orthonormal basis, okay, that solves maximization of UT and summation of U, okay, subject to a condition such that norm is 1. Where summation is the sigma is the data variance, okay, and top k eigen vectors of sigma become the first k principal components, okay. So no class information enters into sigma, and PCA's subspace preserves overall geometric structure, not necessarily the class structure. Okay. LDA's objective to maximize the class separability. LDA seeks a projection matrix W, which maximizes the ratio of between class scatter to within class scatter. Okay. Mhm. Okay. So now you try to see W star. Okay. Argument of maximum, determinant WT SBW. Okay, and determinant of WT SW into W. SB will measure how far apart the class means mu k are, okay, and SW will measure the scatter of samples around their own class mean. Okay. By solving this generalized eigen problem, SBV equal to lambda SW into V, LDF will find the directions that is spread class means far apart while keeping individual classes right. Okay. So your key differences are supervision, okay, unsupervised, supervised, and criterion is maximum total variance, maximize class variance. Okay. Scatter matrices is sigma, and in LDA it is SB and SW, and resulting subspace is orthonormal principal axis, while in LDA it is axes that are optimal for class separation. Okay. And dimensionality limit in case of PCA, it can keep up to minimum of n minus 1 D principal components. And in case of LDA, it is at most k minus 1 discriminant vectors for k classes. Okay. When to use which? PCA is ideal when you want to compress the data, and LDA is best when you know class labels and want to improve the classification. Okay. PCA is your variance maximizer, LDA is your class separability maximizer. That is the distinction why option D, PCA maximizes variance while LDA maximizes class separability is the right statement. Okay. Now coming to the next question, question number 8. Consider a dictionary in 2D space consisting of the following atoms 1, comma 1, minus 1, comma 1, 1, comma minus 1. For a given vector 2, comma 3, evaluate its representation using two atoms of the above dictionary following orthogonal matching pursuit OMP. Okay. Try to compute. I'll be just joining in 2 minutes. Okay. Now if you try to see here, okay, correct option would be your option number A. Okay. First of all, you have to see what is the dictionary of the atoms, which is 1 comma 1 minus 1 comma 1 and 1 comma minus 1. What is the initial residual? It is 2 comma 3. Then first atom selection, you will try to perform the inner products. Okay, D1V, which is 2 plus 3, 5. D2V minus 2 plus 3, which is 1. Then D3V, which is 2 minus 3, that is minus 1. Okay, largest magnitude is with D1. Okay, so we select D1, then we try to calculate the projection onto the D1. Okay, which is nothing but D1V divided by norm of D1 whole square. Okay, so 5 divided by 1 square plus 1 square, that is 5 by 2, that is 2.5. So approximation so far is 2.5 D1, that is 2.5 into 2.5 T.5. Okay, residual is nothing but V minus A. Okay, residual is nothing but V minus A. Okay, which is 2 comma 3 minus 2.5 comma 2.5. Okay, that is minus zero point 0.5 and zero point 0.5. Okay, so for second atom selection, you will be computing dj. Okay, r1 for j2 and 3. Okay, so d2r will be nothing but minus 1 minus zero point 0.5 plus 1 into 0.5, and d3r1 would be nothing but 1 into minus 0.5 plus minus 1 into 0.5, that is minus 1. So again, selecting largest magnitude is with d2. So you try to select d2. Then orthogonal update, since d1 and d2 are orthogonal, so new coefficient is simply d2r1 divided by d2 norm whole square, that is 1 by 2, 0.5. And final representation you will get it v as alpha 1 d1 plus alpha 2 d2, that is 2.5, 1 comma 1 and 0.5 minus 1 comma 1, which is nothing but your option number A. Okay. So orthogonal matching pursuit, or OMP, it's a greedy sparse coding algorithm. Okay, it is used to represent a signal or data vector as a linear combination of small number of basis elements. Okay, or they are also known as atoms, which are drawn from possibly over complete dictionary. Okay, and detailed breakdown of all the things is here. Why it is sparse? Because many real world signals, for example your images, for your audios, for your sensor data, they can be approximated very well using only few building blocks. Okay, for compression, for denoising, and for interpretability, we try to use this OMP technique, orthogonal matching pursuit. Okay, and dictionary is D equal to nothing but collection of all the D's, D1, D2, D3 to DM of a unit norm vector in relation R D. Okay, where M, capital M, is greater than D, the dictionary is over complete in those particular cases. Okay. Basic matching pursuit. Okay, relation R0 is V, the original signal. Okay, and greedy selection at each step K, you pick up an atom DJ. Okay, and that has the largest absolute inner product with the current residual. Okay, argument of maximum RK minus 1 and producted with DJ. Okay, and coefficient is alpha k rk minus 1 djk, and approximate update is vk equal to vk minus 1 plus alpha j djk. Okay, and residual is v minus vk. Residual already we have computed in this particular question itself. Okay, repeat until the residual is small enough or a fixed number of atoms k is selected. In your case, you just have to match with the options. Okay, it would be one or two iterations at maximum. Okay, limitation of MP: once an atom's coefficient is set, it's never revisited. Okay, even if later atoms overlap with it, leading to suboptimal coefficient estimates. Okay, this is your basic matching pursuit. Okay, then orthogonal matching pursuit is somewhat different. In OMP, it improves on basic matching pursuit by re-optimizing all chosen coefficients at each iteration. Okay, such that your residual is orthogonal to the span of the selected atoms. Okay, so you try to initialize R0, then A, and then K, then repeat until small k is equal to capital K, or norm of Rk is small. And in case of your atom selection, Jk plus 1 equal to argument of maximum Dj Rk. Okay, add it to the active set A. Okay, then solve the least squares on active atoms. Okay, and calculate alpha. Then update approximation and the residual. Okay, that you try to solve. Okay, then the solution is alpha equal to the expression that has been given here, and update approximation and residual calculation you can perform, then increment k as k plus 1. Okay, geometric interpretation: at each iteration you are projecting the residual onto the new atom and then reprojecting the original vector onto the entire subspace. Okay, spanned by your selected atoms. Okay, this will ensure that the residual is always orthogonal component left outside that subspace. Okay, so compared with the plane matching pursuit, okay, the OMP will never overcount, okay, directions it has already used. Okay, so now you try to see the computational consideration, the complexity. Okay, it is given by big O notation KMD plus KQ. Okay, M is the inner product over M number of atoms. Okay, and find the sparsity, which is capital K, then residual norm below the tolerance, and sufficient decrease in residual norm you have to obtain. Okay, then when and why to use OMP: in case of your sparse signal recovery, in case of your dictionary learning, in case of your denoising and decompression, in case of your feature selection, OMP is used. Okay, next question number 9: OMP is greedy algorithm, or is it a dynamic programming algorithm? Is it a divide and conquer algorithm? And D, none of these. If you have listened to my conversation in the question number 8, then you would be very easily to able to solve this particular type of question. Okay. Yes. OMP would be nothing but a greedy algorithm. I already told you in question number 8. Okay. Orthogonal matching pursuit is a greedy algorithm because at each iteration it will select the single dictionary item that is most correlated with the current residual. It augments the active set with that particular atom. It recomputes all the coefficients by solving least square problem over the chosen atoms. Okay. It updates the residual to be orthogonal to the span of the selected atoms. This step-by-step locally optimal selection of one atom at a time without backtracking is the hallmark of greedy approach. Okay. Then question number 10. Which of the following are true with respect to KSVD? Okay. It is a dictionary learning algorithm for sparse representation. It is a generalization of k-means clustering algorithm. It works on updating dictionary items until convergence or B, all of the above. Try to solve. Yes, the correct option would be D, all of the above. Okay. KSVD, it's a widely used dictionary learning algorithm. It builds on and generalizes ideas from k-means clustering to obtain the sparse representations of the data. Okay, it's a dictionary learning algorithm for sparse representations. Yes, this is true. Okay, because it learns from a dictionary and sparse coefficient vectors alpha i's such that data sample xi is well approximated by a sparse linear combination of dictionary items. Okay. The next statement was it is a generalization of k-means clustering algorithms. Yes. In k-means, each sample xi is approximated by exactly one cluster atom. Okay, dj. Okay, and you alternate between assigning samples to their nearest center and updating each center to the mean of the assigned points. And KSVD, yes, it generalizes this by allowing multiple atoms per sample rather than a single one. Okay. Then it works on updating dictionary items until convergence. Yes, this statement is also true because KSVD will proceed by alternating between two main steps until the convergence is reached or until a fixed number of iterations is reached. Okay. For a your sparse coding step for a fixed dictionary D, okay, the finding the sparse coefficients alpha I, okay, that will maximize your summation xi minus d alpha I whole square subject to the condition, subject to this particular condition that norm of alpha i's is less than equal to t. And dictionary update step For each atom decay, identify all the samples, form the residuals by subtracting out contributions of all other atoms and compute the best rank minus one approximation. Okay. These two steps iterate, refining the dictionary atoms and sparse codes until the total reconstruction error stabilizes. Okay. Altogether, ASVD will learn, extend, and alternate updates uh, till the convergence is obtained. Okay. Hence, all the statements 1, 2, and 3 would be correct. Correct option would be D, all of the above. Okay. So, this marks the end of the 10 questions which I wanted to discuss. Now, we'll discuss some of the practical aspects. Okay. I'll share my second screen and I'll try to share some of the Google Colab notebooks that I have prepared. Okay. Just wait for me. I think the screen got struck. Yeah. Now I think let me just share my second screen. Okay. Just in a minute I'll share. Yeah. Just 1 second. Yes. Let me just share this. I hope you can see my second screen. Yeah. So here in this particular notebook, what I have done, I have prepared the algorithm, different algorithms, as well as their codes, as well as their implementations for these three particular algorithms: greedy algorithm, dynamic programming, divide and conquer approach. These were mentioned, okay, even in a multiple select question, multiple choice question. Okay. So in order to demonstrate those, I have prepared this particular notebook. Okay. So let me just go a little bit down. Let me first run it. Okay. I think it will take some time to execute. Yes. Okay. It has got executed. No problem. Okay. Let us just see it. Okay. So first of all, you try to understand greedy algorithm. Okay. Greedy algorithm. Then after that, dynamic programming, and after that, divide and conquer, and after that, PCA. Okay. Practically, what is the significance and how in real time you can apply it. Okay. So for demonstrating you the greedy algorithm, suppose you are a cashier and you need to give change of rupees 93 and you have to use the minimum number of coins. Okay. And your available coins are of rupee 1, 5, 10, 20, and 50. Okay. So a greedy algorithm would be nothing but an approach which will work by choosing the largest possible coin each time, leading to an optimal solution. Okay. From a set of solutions, you have to just choose the most optimal solution. Okay. That you would be able to obtain using this particular approach, which is nothing but your greedy algorithm. Okay. So what is the thing? How I have done it? I have made an array. Okay. Coins are 50, 2, 10, 50, 20, 10, 5, and 1. Amount is 93 and change is an empty array. Okay. For coins in this for coin in coins. Okay, while amount is greater than equal to coin, amount minus equal to coin. Okay, means you are just trying to deduce what change you have already given, and then you have appended the change in this appended the change, okay, in the array coin, and then you will try to use coins used is change. Okay, try to print this particular number of coins which you have used. So the most optimal solution will be 50 20 20. Okay, 1 1 1. That will give you 93. I haven't used 50 5 rupee coin, 10 rupee coin. I have used 50 20 and 1. Okay, so this is an example of greedy algorithm. Okay, greedy algorithm, and how in real time you can just try to frame a problem and a solution. Okay, now for your dynamic programming, okay, I'll demonstrate it mathematically also, but first of all, I want to give you a simple example where in real life you can apply this particular concepts. Okay, for your dynamic programming, if you imagine you are climbing a staircase with n number of steps, and you can either climb one or two steps at a time, then how many different ways are there in which you can reach the top? Okay, this is dynamic programming because each number of step will depend on the smaller sub step which you have already taken. Okay, so number of ways, okay, in which n steps would be can be just finished would be ways n minus 1 plus ways n minus 2. Okay, means last two steps you have to just count, and on the basis you would be able to judge how many number of steps, or how many number of sub problems you are able to formulate within that particular problem. Okay, so then you try to define this particular function climbing stairs. Okay, and your this particular function, okay, dynamic programming, in short I have written dp equal to 0 as a single element multiplied by n plus 1. Okay, dp0 is an array and dp1 is 1 comma 1, and then I have used a for loop in your range 2 to n plus 1, and I have written a simple statement that dpi equal to dpi minus 1 plus dpi minus 2, and then I have written the dpn, and ways to climb 5 number of steps would be 8. Okay, directly it is coming. So in this particular type of problems, okay, in which you have to find the number of ways in which a particular task can be handled, and that particular task is interdependent. Okay, then in those particular cases you can use this particular dp or dynamic programming approach. Okay, suppose I want to know how what is the way to climb 100 number of steps. In with those particular cases, just have to substitute 100 in both the places, try to run this cell and see how many number of options you are available with. For 5 number of steps it is 8, for 100 steps it is this particular value. And these type of problems in which the number of steps of executing a particular problem is interdependent or dependent on the preceding or succeeding step, and the problem solution grows exponentially, are known as combinatorial explosion problems. Okay, these are very hard problems in computer science, and the hardest problem till now which has been not been able to solve using uh, there are optimal solutions which have been obtained, but still we are trying to come up with more optimal solutions. Okay, till now the end hasn't we haven't seen, and that particular problem is traveling salesman problem. Okay, and one of the approach to solve that particular problem is this particular one also, dynamic programming is also a particular approach. Okay, so what is the problem? I in brief I'll try to explain. Suppose there are n number of cities in which a person has to deliver m number of letters, and the condition is that such that you only have to visit n cities once at a time. Okay, so for this particular problem there are n minus 1 factorial number of ways, and finding the most optimal way is the challenge. And if you try to calculate for even for the 10 number of cities, it would be 9 factorial. That would be the total number of possibilities. Okay. So from n 9 factorial number of ways, you have to select the way in which the most optimal condition is reached. Okay. So this one is a traveling salesman problem. Okay. And one of the way to solve it is using dynamic programming, and in that particular case also, this type of strikingly high number of ways or number of possibilities are obtained. Okay. Even I type here 50. Okay, still the number would be very high. Okay, see here it is a pretty huge number. Okay, so even for 10 number of steps, it would be starkingly high. Okay, and out of that, you just have to obtain it is 89 for 10, and for 15 manually it is not even possible. It is 987. So even for 15 number of steps to find the most optimal pathway, okay, you have to go through 987 number of steps. Okay, so manually if you are doing it, you won't be able to achieve the optimal condition, okay, within due course of time. So that is why you go for programming. Okay, dynamic programming is there that will give you a set of optimal solutions. Okay, then divide and conquer. Okay, suppose you are searching for a word in a dictionary, then instead of reading line by line, you open a book in the middle and decide whether the word lies in a left half or right half. Okay. This is the same approach which is there in sorting also. Okay. So same approach we are just trying to build up here. Okay. Similar to the our sorting approach. Okay. Just 1 second. I think it got hanged. Yeah, it is back. Yeah. So for divide and conquer, okay, you are searching, you are opening a book into the middle and deciding whether your word lies in left half or your right half. Okay, this is the same approach which is there in your binary search. Okay, so low and high. First of all, I have created a function. Okay, that will take the input as array and the value which has to be just found out, which is x, and low high to number of temporary variables I have created, which I have just initialized by 0, and I have found out length of array minus 1th element because the indexing in array starts from 0 in Python. Okay, while low is less than equal to high, then mid value is low plus high divided by 2. Okay, then if array mid equal to x, then return the mid value, and if array mid is less than x, then low equal to mid plus 1. Okay. We are not doing anything, we are just passing an array, and then we are coming towards the midpoint, and whether we are deciding, since the array is sorted in ascending or descending order, so we are deciding on the basis of that in which direction we have to move. Either we have to move in forward direction or we have to move in backward direction, or left direction or right direction. That is what we are trying to do. Okay, so if you pass an array like why is this, okay, and you try to find out any element. Okay, suppose here I have found out 7. Okay, if I try to find out 13 from here, I will be still able to do it. Okay, see, indexing is 6. 1, 2, 3, 4, 5, 6. Okay, index is 6. Index in Python starts from 0. Okay, so 0, 1, 2, 3, 4, 5, 6. That is why it is saying index is 6. Okay, if you want to know the exact place, then you have to uh, just add 1 to the value. Okay, so if I try to modify it, array find 13 at index, in place of index I write place, then I have to add 1 here. Okay, place is 7. Okay, indexing is 6. Okay, So this type of modification you can perform in order to improve the user interface of your program. Okay. Then for PCA, suppose each student, the practical demonstration I am performing first, then I'll delve into more complex examples. Okay. For principal component analysis, suppose each student in a class is having four scores. Okay. Math, physics, chemistry, and English. And you want to visualize the student's performance in just two dimensions. Okay. So for reducing it from four dimensions to two dimension while still keeping the maximum variation in scores, you can use this particular attribute, okay, or particular facility, which is PCA, principal component analysis. And where you will find it out in sklearn. Okay, sklearn is a particular library in Python. Okay, then here I have not installed it because it is already installed in Python, in Google Colab, in Python 3 interface. Okay, if you are using Jupyter notebook or any other Anaconda notebook, okay, Anaconda interpreter, or you are using Spider IDE or Eclipse IDE or any other IDE, then you have to install the library first. But since it is pre-installed in Google Colab, that is why I haven't used it. Okay, I haven't installed it yet. Okay, so that is the thing. Import and numpy as np, import matplotlib pyplot as plt. Then from sklearn dot decomposition import pca. Okay, then student scores directly as an array we have supplied 90, 85, 88, and 70. Then 72, 60, 65, 80. These scores we have applied. Then we have to perform the dimensionality reduction, and I have just called the function, okay, and use the fit transform to transform it from four dimensions to two dimensions. Okay. Even I can do it for one dimension also. I'll just try to do it and then try to see here, okay, what result I'll be getting. Then I have plotted this particular function. Okay. Codes are reduced from 2D, uh, reduced from 4D to 2D with the help of PCA, and the two principal components PC1 and PC2 I have obtained. Okay, and PC1 is able to accommodate 82.9% or 82.89% of the variation in the data, and PC2 is accounting for 13.04 percent variation in your data. Okay, so if you still try to want to compute, okay, any one principal component from reducing the dimensionality from 4 to 1, you can still able to do it. Okay, just you have to perform this particular operation and then try to compute it, and you have to just delete here pc plot.y label. Okay, pc2 you just have to delete it. I'll just run it. Okay, it will show me error. Okay, why is it showing error? Because I haven't reduced the dimensionality in lines below. Here also I have to use reduce the dimensionality. I have to remove this particular part. Okay, then only it will be reduced to one dimension. Okay, so since 82.9% of the variability in the data I am able to explain using only one principal component, so my results are satisfactorily all right. Okay, so this one is the demonstration of your principal component analysis and your principal component reduction, and using a simple example and using the sklearn library I have demonstrated you. Okay, and the more manipulation, reducing it from 2 4 to 3, then 3 to 2, then 2 to 1, that you can try. Okay, just get this notebook and try to run it. Okay, meanwhile you will get a hands-on experience, okay, how to do that, which components you have to delete and which components you have to use. Okay, then just one second, I have to minimize this. Yeah, then this is the notebook which will explain you greedy algorithm, dynamic programming, divide and conquer, okay, in detail. Let us dwell it. Okay, simple example, I already told you what is the simple example. Okay, already taught you that. Now you try to see greedy algorithm will try to build up a solution piece by piece. It will always try to choose next piece that will offer the most local optimal choice or most immediate benefit. Okay. And the example is Huffman coding, which is used in data compression, like in your JPEG or like in your MP3 or zip. Okay. Greedy choice will ensure that shorter codes are assigned to more frequent symbols, minimizing the average code length. Okay. Other examples used in research are minimum spanning tree and Dijkstra's algorithm. Yeah. Dijkstra's algorithm is nothing but a path planning algorithm which is used to calculate the shortest path. Okay. Used to calculate the shortest path of a weighted graph. Okay. Then in but this particular example, I have just used Huffman coding with greedy choice. Okay, with greedy choice. Then this particular library I have to import, which would be having this Huffman code example. Okay. Then I have imported counter, then name tuple, then I have created a class, okay, named node, then created a class named leaf, then Huffman dot encode. Okay, I have used. Then I have used it for code encoding. I have just obtained the codes and I have printed those. Okay. So for any text, you can just try to convert it into Huffman codes. I'll just try to give you a brief idea about Huffman codes also. In your computer science, Huffman code is a particular type of prefix code that is used for lossless data compression. Okay. It might look to you that it is not getting compressed, but trust me on this, it is actually getting compressed because if you try to store each alphabet, okay, and then you try to see the number of alphabets, then you will get a very long binary composition, okay, of digits. But it is itself getting compressed here. You can trust me on this. Otherwise, you can try to see here that 16 number of bits or 8 number of bits would be reserved for just one alphabet. Okay. And then you try to see how many number of alphabets we have tried to store. So that would be a very long chain of binary values. So that is getting reduced actually here. Okay. So a Huffman code is a particular type of optimal prefix code which is used for lossless data compression, and the process of finding and using such Huffman code, which is developed by David A. Huffman, okay, student at MIT, was published in 1952. Okay, and this particular one is the tree, okay, which is coded. Okay, each and every alphabet we have just tried to code, okay, into a binary code, okay, consisting of zeros and ones. Okay, and this is the particular terminology. Then what is the example you can see for yourself. Okay, very interesting problem, Huffman coding problem. Okay, used for lossless data encapsulation or encoding. Okay, that I have tried to demonstrate here using a particular working example and a particular word. Okay, so if I try it for another example, for example computer vision. Okay, you would still be getting computer space vision. Okay, you would be still getting Huffman code. Okay, so try to use it, try to obtain the Huffman codes. Okay, based on greedy algorithm. Okay, then for dynamic programming solves problems by breaking them into overlapping subproblems, storing their solutions to avoid the recomputation. Okay, already we have seen how this particular approach works. Okay, it works when a problem has optimal substructure or overlapping subproblems. It builds a solution by memoization or tabulation. Either it chooses a top-down approach or a bottom-up approach. Okay. For protein research alignment, okay, it was used in bioinformatics to align the DNA sequencing, find out what is the most optimal sequencing. Okay. Uses dynamic programming to find optimal alignment by comparing the subsequences. Okay. Other examples in your research are speech recognition, NLP, natural language processing. Okay. Then finding out in this particular example, okay, we are finding out the most common the longest common subsequence. Okay. So we have defined a function LCS x and y. Okay. And we have found out the length of x, then length of y. Then I have calculated this particular function, dynamic programming, in short DP. I have written 0 into n plus 1 for int for I or for the variable in range m plus 1. Okay. Then testing with the DNA sequencing. Then for I in the range, for j in the range, for two for loops I have used. And then if xi equal to yi, then I have moved it. Then I have added it in the sequence. Okay. Else I have used the maximum possible value of the sequencing, and then I have tested it with sequence like these two particular one AC GT GT GCA and GT GAC. And what is the longest common subsequence I have obtained here in this particular case? It is 4. Okay. Next, divide and conquer. In case of your divide and conquer, we apply the particular possibilities. Divide, we split the problem into smaller subproblems, then conquer. We try to solve subproblems recursively, then we try to combine or we try to merge the solutions. Okay. For your research example, it is fast Fourier transform. Okay. It's a it revolutionized the signal processing, reducing the complexity from big O notation n square to big O notation n log n. Okay. And it is used in medical imaging for MRIs and CT scans, astronomy and audio processing. And other examples in research are merge sort and binary search, okay, which are having the computational complexity respectively as big O notation n log n and big O notation log n. Okay. Then merge sort for using divide and conquer approach. This particular function I have used. Okay. Sorting, it is nothing but the operation of arranging the array values either in ascending or descending order. Okay. So for merge sort, you can apply this divide and conquer approach and you can write the function likewise I have written, and then I have tested it with a unsorted array and I am able to sort it. Okay. So you try to see here using merge sort. Merge sort function. Actually, it is a very long function. Okay. And I am able to reduce it using the divide and conquer approach. Okay. So how I am able to do it, just try to see here in this particular notebook. And if you get any inspiration, then you can also try to build your own function for sorting. Okay. Even for sorting or as well as for any research problem, you try to uh, you try to in just be try to be somewhat innovative and try to solve a particular problem. Okay, using this particular divide and conquer approach. And one more thing I like to tell you that nowadays artificial intelligence is getting uh, its stem in each and every field. Okay. Even in computer science nowadays, people are saying that 90% of the code is written by AI. Okay, so no human interference is required and blah blah blah. Okay, all these things you must have heard as well as read in various of the platforms. Okay, but my sincere advice to you as a student as well as a teacher of this particular domain would be this simple advice that wherever it comes to innovation that the world hasn't seen, AI will be failing very badly. Okay. So only humans have got this potential that they can invent something which hasn't been invented till yet. And if you want to get a good job as well as you want to maintain your decorum in this particular domain, you have to keep on inventing, and reinventing the wheel would be the only thing which will help you to survive in this cutthroat competition in which a lot of people are getting laid off just because some AI tools are there which can do their amount of work in seconds. Okay. So this is a simple career advice to you all. Okay, as a feature of this particular domain I am telling you. Okay. Next, summary is this: simple, greedy algorithm is simple, it is efficient, works on local choice, okay, and dynamic programming, it stores solutions of overlapping subproblems, okay, and divide and conquer, it is recursively breaking down and merging. Some extended examples you can see, for example, your Dijkstra's algorithm, okay, it tries to find out the shortest path in a graph theory problem, okay, from start node to the end node. What is the shortest path, okay, related to path planning problem, okay. So I have created a particular graph and try to provide the weights on the node, okay, and then what is the shortest path I have tried to obtain using the greedy algorithm, okay. So here you just try to, if you try to manually see it, graphs are defined like this, okay. Generally, the students face a problem in graph theory. Okay, graph theory is a particular course which is taught to you in, I think, third semester. Okay, third year. Okay, third year, first or second semester, it would be taught to you. Okay, so students face a general problem in defining the graph itself. How to define the graph? Okay, so here the notation which in which I have written, it is very simple to understand that node A and B are connected and the weight in between those two particular nodes is 4. Similar to that, node A and C is connected and weight in those particular nodes is 1. Now B and E are connected and the weight is 4. Then C and B are connected and C and D are connected and the weights are 2 and 4. Then D and E are connected with the weight 4 and E is the last node. So similar to that, you can try to always build a graph yourself and try to calculate which is the shortest path and what is the total amount of cost. Okay. So in this particular case, the shortest path sequence which I have obtained is A to B, then C, then D, then E. Okay. That is the shortest path from A to E. Okay, so similar to that, you can just try it with another approaches also. Okay, brute force is also an approach, which is you can apply and try to obtain what is the shortest path from source node to the goal node. Okay, then knapsack problem. Yes, this is also a very famous problem. Okay, knapsack problem is there, which is there in which the principally is faced in optimizing cargo space and airlines in project selection and economics. Okay, so what is knapsack problem? Knapsack, as the word suggests, okay, knapsack, as the word suggests, is it is a bag. Okay, suppose it is a bag which has to be filled most optimally in order to accommodate the baggages of various sizes. Okay, so how to select those particular baggages and which to select and which to deselect, okay, or which to reject, that is dealt in the particular knapsack problem. Okay, and various approaches are there. Okay, and practically it has been seen in speech recognition and DNA sequencing. Okay, so knapsack problem we have defined weights, okay, values and W, and just like I have defined it for your graph theory problem or your Dijkstra's algorithm, this similarly we first have to define the problem and then we have to just try to calculate it, and the maximum if I go for this particular combination, weights are 2 3 4 5, values are 3 4 5 6, okay, and maximum number of values which would be present in the knapsack would be 7, that I have tried to obtain using the dynamic programming, and the function is there in front of you all. Okay, next, divide and conquer. Okay, this particular approach I have used for fast Fourier transform, which is there used in image processing, in astronomy, in biomedical engineering. Okay, Fourier transform in general is a very important concept, and practically it is used in optimization. Okay, practically it is much used in your optimization. Okay, so try to recall its formula. What is the principal application? I have used it here. Okay, divide and conquer using fast Fourier transform. FFT, I have built a function, then signal I have provided, and then what is the fast Fourier transform of that particular function I have obtained. Okay. Then for PCA also same concept using on the iris dataset, which is most commonly used for machine learning research. I have used it. Okay. Principal component analysis is used for dimensionality reduction. Okay. It will try to find out new axis. Okay. That will maximize the variance in data, minimize the redundancy. Okay. It is useful because of high dimensionality data is hard to visualize and computationally expensive also. Okay. Its application lies in genetics, then image compression, then finance and medicine. Okay. Goal is to demonstrate PCA using the iris dataset, and I have accomplished it using this particular function. Okay. Try to see here directly I have loaded the iris dataset because it is already present in your sklearn. Okay. And then I have applied PCA. Okay, directly I have already demonstrated how to apply it, and you just have to call the function and provide the number of components. Then you have to fit transform. Okay, then you try to plot the results, and then you try to say what is the explained variance ratio. Okay, in this case, two principal components I have tried to plot them down. Okay, and 92% of the variation in the data is I am able to obtain using the first principal component. Okay, and likewise these examples I have demonstrated. Okay, so this is the end of this entire notebook. Okay, humble request to you is just get it. Okay, after you complete all the 10 questions. Okay, and revise all the concepts which I have taught till yet. Okay, humble request to you is just get this notebook, try to run it down, try to place with the parameters. Okay, and then you will be getting a hands-on experience on how this particular concepts are dealt. Okay, so this marks the end of the 10 questions as well as the uh, Google Colab notebook which I wanted to discuss. Okay, thank you all for joining the session. Okay, thank you very much and all the very best for your examination. Keep on revising the concepts. Okay, two more sessions are left. First, I will take the session week number 12 in the next on the next Saturday, and just day after that. Okay, I think day also I can tell you on 12th of October there would be another 2 hour session of summary session. Okay, in which I will be summarizing all the concepts which I have spoken from week number 1 to week number 12. Okay, that will complete the entire syllabus from week number 1 to week number 12 along with the summary sessions. Okay, this is what you will get from my side. And for the examination, okay, please revise all the video lectures, all the notes which are there as a PDF. You can get it. Okay, in the transcript section you would be able to get those notes. Okay, try to take them down, revise. After that, try to go through the sessions PDF. Okay, and if you are having time, you can even go for videos. Okay, so those PDFs you just try to get those and try to revise what are the different concepts. Okay, which I have talked in front of you. Okay, and then you would be very thorough with the entire syllabus. And after that, I think you would be able to solve each and every question which you would see in the examination. Okay. So this is my planning and this is my way, okay, in which I want you to proceed. And thank you so much for joining the session. Okay, this session is ended from my side. If you have any doubt, feel free to ask and do join the session next week, same time, same link. Okay, thank you. Thank you all.
Thank you, sir.
Okay, thank you so much. I'll be still here for 11 more minutes. Okay, still, if you have any doubt, feel free to ask. Okay, else you can kindly leave. Okay, and do join the session next week, same time, same link. Okay, yeah.